All right, so finally, we're going to talk about unit vectors, position, velocity, and acceleration vectors, and then we're going to apply that to a relative motion problem. So, a unit vector is simply a dimensionless vector. It has no units, and it's going to point either in the x or the y direction for this class. There is a z direction, but right now we are doing two dimensional. This unit vector will be represented with a little hat. It has a little caret over the letter, so this symbol instead of an arrow. We can multiply unit vectors by scalars, and when we do this, it's going to change either the length, so the magnitude, or the direction of our vector. So in this case, we have vector A, and if I multiply that by a value of 3, we'll see that it's as if I have 3 vector A's just all attached together. So it multiplies that length by 3. And if I make it negative, it simply flips the direction. Okay, so a position vector, and this is going to be very useful. The first thing I want to point out is that a position vector is going to be denoted with an R, not with an X like we were using previously. So when we're talking about vectors, the R represents position. So a position vector will point from a particle or object's origin. So in this case here, and that's because we drew this coordinate system. So here was our origin. And it will go to the location in question. So we see our initial position and we see the final position. And the change in position is simply this vector here. So we will draw the tail of the displacement vector at the head of our initial position, and we will draw the head of the displacement vector at the head of the final position. So, I hope that makes sense. We also have an average velocity vector, and you'll recall that the velocity is just equal to our change in position over our change in time. And remember, we are now using an R to represent our change in position. So we have our initial position, we have our final position, and we know the times involved with that. So simply connecting those 2 points with a vector, that is going to be our change in position, and it would be our change in time. But those values will be different, and that's going to tell us our average velocity vector. So it is going to point in the same direction as displacement. Instantaneous velocity, on the other hand, is going to involve the tangent lines for some given point in time. So maybe at this point in time, our velocity is moving in this direction, and later on, it might be moving in that direction or this direction. So we'll always be looking at some point in time, and it will be the line tangent to the pathway instead of connecting 2 points together. And we're going to look more closely at this when we work a problem. The average acceleration vector, and again, we can recall from the previous unit that acceleration is found by looking at our change in velocity and dividing it by the change in time. So we have our initial velocity, which is moving in this direction, and the final velocity, it's over here, and it's actually moving in this direction. I've just simply pulled it over so that the tails of both vectors are connected, and that allows me to find my delta V. And the delta V will start, so the tail of the delta V will begin at the head of the initial velocity vector, and it will end at the head of the final velocity vector. And our average acceleration vector is going to point in the same direction as the change in velocity vector, not the final or initial velocity vectors, but that change in velocity. And here's another look where I've actually taken these images apart. So we had our initial vector heading here, the initial velocity in this direction, the final velocity was in this other direction, and I simply put them together. So I took this and I moved it over here so that the tails were connected like this, and that allowed me to draw my delta V, and then we could do calculations with it when we got some values in there. Okay, so let's look at a pathway that has both velocity and acceleration vectors so we can make note of what is happening. So we have points 1, 2, 3, and 4, and I'm going to explain points 1 and 2, and then I'm going to give y'all a moment to think about 3 and 4 before explaining those as well. So here at point 1, we see that acceleration and velocity are headed in different directions, which means that at this point, point number 1, the particle is slowing down because acceleration is headed in the opposite direction as velocity. So this particle is moving in this direction, but it is slowing down. Okay, we get over here to point number 2. So the same point on the pathway, but now it's at this location number 2. And the acceleration vector tells us the direction that that particle is moving. So we can see that this particle here was slowing down, and now it's going to start turning to the left. And that makes sense according to this little pathway here. I hope you noticed that the velocity vector, while it did change directions, it appears to be the same magnitude. So it seems that the velocity is consistent at both of these points. And we would need actual values to verify that because we can't really tell from this graph, but it does appear that way. Okay, so take a moment to think about 3 and 4 and hit play when you're ready. Okay, so for position number 3 for this particle, we see again the velocity appears to be of the same magnitude from the first and second points on this graph. And the acceleration is now taking this particle to the right. So this particle is now turning to the right. And as we continue along the pathway, we see that at point 4, our acceleration and velocity vectors are in the same direction. When that happens, we know that the particle is speeding up. So we can see here that that velocity vector increased dramatically because it's now speeding up. And to end this, not to end this, but to end this portion, let's look at a problem. A car is traveling and it has an initial velocity of this. So we immediately see that the initial velocity has both an x and a y component. 8 seconds later, okay, so we know our change in time, the final velocity is this, and now it only has a y component. So we want to know the magnitude and direction of the average velocity the average acceleration during those 8 seconds. Well, please recall, the average acceleration is just going to be equal to the change in velocity divided by the change in time. So let's start by finding that change in velocity. To find the change in velocity, we need to take v final minus v initial. So let's do that. And we'll be factoring in that there's multiple y hat portions and only one x hat portion. So in our final answer, we should see that 6.36 meters per second in the x hat direction and 8.64 meters per second in the y hat direction. And I just realized this should say 15. There's an extra 1 here. Please ignore that 1. It should be a 15. Okay. Second step. Let's just go ahead and divide this by our change in time, which is 8 seconds. Okay. So we plug in this information on top. We have 8 seconds on the bottom, and we solve to find this. So we still have an x hat and a y hat direction. And you'll see that our units have changed. So velocity is just meters per second, but once you divide that by time, we get meters per second squared. And finally, the last step, we need to find the magnitude and direction angle of that average acceleration. And to do this, we're just going to do what we've previously been doing. So we are going to use that Pythagorean theorem to find our magnitude for acceleration. Okay, so it had both an x and a y component. So we're going to place the x portion here and the y portion here. And then we'll just take the square root of that information to find the average acceleration, which is 1.34 meters per second squared. And to find the angle, it's going to be the inverse tangent of the y component divided by the x component. So inverse tangent of 1.08 divided by 0.795, and that will give you a final angle of 53.6 degrees. And this is our final topic. It is relative motion. So the man who is on the ground is going to see the passenger on the train moving at different speeds depending on this passenger on the train, on his motion. So in this first image, we see that the passenger on the train is moving in the same direction as the train. So both of them are headed towards the right here. In this second image, we see that the man on the train is walking in the opposite direction as the train is moving. So in this case, the man on the ground is going to see this passenger on the train moving at a greater velocity than this man who's walking in the opposite direction of the train's velocity. Okay. But we can also put numbers with this, and you will be doing this in just a moment. So the man on the ground, his perspective, which I'm going to label as PG, the perspective of the person on the ground, is just going to equal the velocity of the person on the train plus the velocity of the train on the ground. And we are about to work problems with this. So we are in a boat, and that boat's speed relative to the water, so how quickly it's moving on the water, is 6.1 meters per second. The boat points at an angle of 25 degrees upstream, that word's going to be important, on a river that's flowing at 1.4 meters per second. And we want to know the velocity of the boat relative to the ground. So if somebody were standing on the ground, what would it appear, or what would the velocity of that boat be to the person on the ground? Let's start with a quick sketch. I did not draw this. Again, we know it was a disaster when I was trying to write on the screen, but I'm going to get that fixed. So here is an image. Yours may not look like this. It definitely won't look like this, but that's okay. As long as you have a rough sketch, you should be good to go. So let's go ahead and work this problem. Well, we're using the same information that we saw over here. We're just going to switch these subscripts to fit our new problem. So the velocity of the boat to the ground. So if somebody were standing over here watching this boat, what they would experience is equal to the velocity of the boat on the water plus the velocity of the water to the ground, which in this case would just be our current. So let's use the piece of information that's going to be the easiest first. When we look at our sketch, we see that the current is flowing in the y direction, which means it does not have an x component. So let's just go ahead and plug that information in. You'll see that this is a negative value, and that's because of this word upstream. The boat is moving against the current, so we needed to make this value negative. Okay, but now we need information for the velocity of the boat on the water. And because it's headed at an angle of 25 degrees, we know that this is going to have both an x component and a y component. So we're going to have to solve for both of those. And we're going to do this just the same as we were doing earlier. We're going to be using the fact that x is equal to the magnitude multiplied by the cosine of theta, and y is equal to the magnitude times the sine of theta. So let's just plug in our information. Okay, so our magnitude in this case, right here, 6.1, and it's the cosine of theta, which is 25 degrees in our case, plus, here's the information for the y component. And when you've done this math, you should have this answer. So now we are ready to plug in our values to our original equation. And when we do, we're going to have to subtract the y values. So we end up with a velocity. The velocity of the boat with respect to the ground has both an x and a y component. So if somebody were standing over here, they would see the boat moving in both the x and the y direction. So yes, it would appear to be coming towards them, but it would also appear to be moving upstream. And that is it. So over these two presentations, these were the big ideas that you should have taken away, and you should be able to work problems with each of these. And finally, here's just a quick summary if you need to go back and review any of this information. If y'all have any questions, please reach out to me. Thank you.